introduction rather, before we get into this, we're going to speak about how we get that resting membrane potential. What are the steps that happen in a process? What are the steps that happen in a cell theoretically for us to arrive at that -70 value? How did we get there? How did we get that -70 charge inside the cell with respect to the outside of the cell? And in order to do so, we're going to do so in a hypothetical way. We're going to first describe the movement of potassium only. So we're going to take a hypothetical cell, right? We're going to pretend that this cell is only permeable to potassium, and we're going to describe its movement first. Then we'll speak about a hypothetical cell where only sodium can move, and we'll describe its movement in that cell. Right now, in our actual physiology, we don't have cells that are only permeable to one of these ions, but in a way to lead up to that conversation of determining and establishing the resting membrane potential, we're going to speak about two hypothetical cells, and then we're going to kind of combine it and put those two pictures together. So first, describing our hypothetical cell where only potassium is moving, right? So this is a cell that's only permeable to potassium. And we're going to rely on our understanding of those driving forces once again. So we've got a chemical driving force for potassium trying to move it out of the cell. And just as a reminder here, the chemical driving force is based purely on the concentration gradient. So we've got lots of potassium in the cell, less potassium outside. And so we have a driving force, a chemical driving force, moving potassium outside of the cell. So that allows potassium to diffuse outside of the cell according to its chemical force. The second part of that picture here is that as potassium moves outside of the cell, it leaves behind that unopposed negative charge. Remember, we just described the fact that potassium is being balanced out on the inside of the cell by the presence of those negatively charged anions, okay? And so as we move more potassium out of the cell according to its chemical force, we leave behind the unopposed negative charge of those anions on the inside of the cell. That initially allows the inside of the cell to become more negative, okay? That's kind of the first part of the equation. We now can introduce our second driving force, our electrical driving force. The electrical driving force now is going to try to move potassium in the opposite direction, right? We now have an unopposed negative charge inside of the cell. Potassium is a positively charged ion, and so we now have an electrical force trying to move potassium back into the cell towards the unopposed negative charge. And so but we can see here that we have a chemical force moving out, but an electrical force moving inward, okay? And so again, we're going to rely on something that we've spoken about already. When we have forces moving in opposite directions, we then need to think about the equilibrium potential for this ion and compare that to the membrane potential at this time, okay? So the cell eventually is moving and it's going to reach its equilibrium potential, right? It's equilibrium where there's no longer any movement, and that's going to be a membrane potential of -94, okay? So this is going to be when the cell has when potassium has equal and opposite forces trying to move it in both directions. It's got a chemical force trying to move it out, and it's got an electrical force trying to move it back in, and those forces are of equal magnitude, so potassium is no longer moving, okay? It's at equilibrium. And so when an ion is at equilibrium, we said that there's no net force for it to move across the membrane, right? The chemical force is equal to the electrical force, and so there's absolutely no movement because the electrochemical force, which is the combined sum of both of those forces, is equal to 0, right? This is all pretty much a review of what we've already spoken about in Unit 1. So that's our first hypothetical cell, right? We've got movement of potassium out according to the chemical force, movement of potassium in according to the electrical force. Potassium eventually gets to equilibrium where there's no net movement, and that is at -94, right? That's how we get to potassium's equilibrium potential of -94. Let's now look at our another hypothetical cell where only sodium can move, okay? So we're thinking about a hypothetical cell only permeable to sodium, and we're reminding ourselves about the relative contribution of ions on the outside of the cell. So we've got sodium outside of the cell, right? Excess of sodium outside of the cell, And we also have chloride kind of balancing out that charge. Chloride is an anion, and so it's going to kind of balance out that positive charge that's on sodium. So let's now think about the movement of sodium here. So we start off once again with our chemical driving force. And because of our concentration gradient, we have more more sodium on the outside of the cell, less sodium on the inside of the cell. We have a chemical force or a chemical gradient that wants to move sodium onto the inside of the cell, right? That's going to be high to low concentration movement. Now, as sodium begins to move according to its chemical force, we then leave an unopposed negative charge on the outside of the cell. Remember all that chloride that was being balanced out by the presence of sodium. So as we move sodium into the cell, according to its chemical force initially, we leave this unopposed negative environment on the outside of the cell. And so we now want to introduce our electrical driving force. So because we have sodium wanting to get to the negative environment on the outside of the cell, we have an electrical force acting in the opposite direction, okay? So a chemical force trying to move it into the cell, an electrical force trying to move it back out of the cell where it can be attracted to the unopposed negative charge that is created by the chloride that is remaining outside the cell, okay? Now the cell again eventually reaches equilibrium, and equilibrium is, just to remind ourselves here of the terminology, equilibrium is where we no longer see movement. So all the movement kind of evens out, and then we think about what is the membrane potential at this time. So for sodium, when sodium gets to its equilibrium, the cell is actually at a positive membrane potential, and that value, sodium's equilibrium potential, is positive 60 millivolts, all right? And again, what that means is at that membrane potential, at the membrane potential of positive 60 millivolts, sodium's chemical driving force is into the cell, the same exact magnitude as its electrical driving force, which is out of the cell, okay? And so sodium is no longer moving at positive 60 millivolts. All right, I'm gonna pause here. Please let me know how we're doing with that so far, right? We want to make sure everyone's still on the bus before we keep moving. So let me know if I've lost you at any point in speaking about those two hypothetical cells.
So the chemical and electrical driving forces are necessary to keep the cell at equilibrium?
Yes, that's true. So the chemical and electrical driving forces both are acting on that particle and allows it to reach its equilibrium, right? When they both become the same magnitude in opposite direction, that is where we get that equilibrium value from.
Okay. What kind of anions are found inside the cell?
These are usually organic anions. I don't have specific names for those, but there's a lot of different types of anions that can be found outside that are negatively charged. Sometimes proteins also exert a negative charge as well. So there's a lot of different substances that are negatively charged.
Okay, so it's not just chlorine. Well, obviously it's not just chlorine, but I was just wondering if there was like an element of some sort.
No, there's not a specific element. It's just like they're just lumped together as negative charge. This is going to be on the inside of the cell. Chloride is going to be on the outside of the cell, opposing the charge of sodium.
Okay, so can chlorine get inside the cell?
Chloride does move. Yep, we'll talk about chloride movement. It does move, but it's not the ion that we're speaking about in terms of opposing potassium charge. We're talking about the ions that are at excess. So chloride is also at an excess on the outside of the cell.
Okay.
Okay, hope that makes sense. Any other questions? Those are some good questions. Any other questions? Okay, so now we're thinking about the electrochemical forces and really, again, combining the forces here. So we combine the electrical and chemical forces on sodium, and due to its initially due to a stronger chemical force, but the electrical force will continue to increase, and that's where we get that equilibrium potential of positive 60 from, right? It's gonna be a really positive value, and that is actually going to indicate the movement of sodium, which we'll speak about a little bit later on, okay? So now we're thinking about kind of putting all of that together, right? We've got sodium moving out of the cell, potassium moving out of the cell, sodium moving into the cell according to their chemical forces, right? We're thinking about the chemical forces only here. So sodium into the cell, potassium out of the cell, right? Based upon our hypothetical discussion previously. And so the membrane now becomes more permeable to potassium. We said that, remember, a resting neuron has more potassium channels. We can think about this as more potassium doors. And so that is a reflection of the increased potassium permeability, right? We can see that reflected here. So there are 3 potassium channels on the apical or on the top surface of this cell, and 1 sodium channel on the bottom surface of the cell. That's going to be really important to understanding why we see the movement that we do, right? So make sure that you're remembering that. There's more potassium channels, which creates more potassium permeability. So this allows more potassium to leave the cell than sodium can enter the cell, okay? So as we're seeing here, because there's more of these channels and we have a concentration gradient, potassium wants to leave the cell, but it can do so through more of those doors. Sodium, on the other hand, wants to get inside the cell, right, according to its concentration gradient, but it cannot do so because, as it cannot do so in the same way that potassium can, because we have less of those sodium doors. I hope that makes sense. And so as we see the movement of these ions, according to their driving forces, but also thinking about the relative permeability of these ions, we then start to get this negative environment on the inside of the cell, right? Less positive charge coming in, more positive charge leaving as we have more potassium channels and less sodium channels, okay? And so now we think about the electrical forces here now, right? We're now adding on that piece of the electrical forces acting on these ions. So potassium has an electrical force moving it back into the cell because we now have a negative environment inside the cell, positive environment outside the cell because of those varying permeabilities that we just described. So now potassium wants to get back into the cell, but sodium also wants to get back into the cell, right? They're both positively charged ions. And if we're only thinking about the electrical force, both of these ions will want to try to get back into the inside of the cell where we have a negative environment, okay? So the forces that develop is sodium moving into the cell according to its electrical force, and potassium also moving into the cell. Sodium moving into the cell according to its electrical force, potassium also moving back into the cell according to its electrical force. And that is going to create the fast movement of sodium into the cell, right? And the slow movement of potassium outside of the cell, okay? And just to take us back to the fact that we're combining these forces, and based upon what we've said about combining forces, if the forces are acting in the same direction, we simply add them together and the ECDF will be in that general direction. So because sodium has an inward chemical force, it's also got an inward electrical force, it's going to have a really strong inward force because we're combining those forces. So that's a really large magnitude, and then the overall direction will simply be inward. Potassium is a little bit more tricky, right? It's now got forces in acting in opposite directions. It's got a chemical force moving outward, an electrical force moving inward. And so what do we do when we have forces acting in opposite direction in terms of determining the magnitude?
You subtract the lower from the higher.
Excellent, thank you. We subtract the weaker force from the stronger force, right? The weaker force here is the inward electrical force. The stronger force is the outward chemical force. And again, I keep going back to our algorithm that we drew out because it's so important in understanding this. We know that this is the weaker force because we're looking at the equilibrium potential. Remember we said if forces are acting in opposite direction, the next thing we want to turn our attention to is comparing the membrane potential to the equilibrium potential. If the membrane potential is -70 and the equilibrium potential is -94, the equilibrium potential is a bigger value, it's a bigger force. And so the overall ECDF will favor the stronger force, which is the chemical driving force. And so we simply subtract that weaker electrical force from the stronger chemical force, and we get a smaller value, but a general net direction favoring the chemical driving force, okay? And so basically looking at our ECDF of potassium now, we're gonna see an outward direction, but we're gonna see a very small magnitude. And that's where we get the slow outflow of potassium from, okay? And I often see students confuse this with the permeability. So we're not really speaking about the permeability at this point. We're speaking about combining our two forces. They're acting in different directions. And so we subtract the smaller force from the larger force until we get a smaller value, which means that potassium will be moving outside of the cell, but it's going to be doing so in less of a forceful way, right? It's going to be trickling outside of the cell. Whereas sodium, on the other hand, because we combine the forces, they're in the same direction, we're going to get a bigger magnitude. We're going to get a stronger force. So sodium really wants to get into the cell, right? It's a stronger thrust for sodium to move in the cell, whereas there's a weaker sort of trickling of potassium outside of the cell, according to combining those two forces. All right. Okay. And then at that point, we establish a steady state. So a steady state is where we get to this, this condition where there's no longer any net accumulation. The inflow of sodium is balanced by the outflow of potassium, right? Because if we think about this, sodium has a stronger force to get into the cell, but it's got less doors or less channels to do so. Potassium has a weaker force to get out of the cell, but it's got more opportunities, right? It's got more doors, more channels to do so. And so that brings us to this steady balancing of both of those ion movements. So the thrust of sodium into that one channel is balanced out by the trickling of potassium through many channels, okay? And then we arrive at that steady state. And that is exactly how we establish our resting membrane potential, okay? So that's kind of walking us up to how we get that -70. So when we get to the steady state where although ions are moving right in and out, according to the sodium potassium pump, according to these channels, we're not accumulating anything on either side. We just have this steady state. Inflow is balanced by outflow is balanced by inflow, and we continue to maintain that -70 millivolts inside the cell. That's how we get our resting membrane potential.